Okay, so I'm Schwartz. Probably some of you know me from my years at Percona, where I was for a few years before I founded VividCortex in 2012. I've just talked about VividCortex, so we can skip that. That'll be only for the records. I will give them in these slides to post. Screenshot of VividCortex, we can skip that. So what I'll talk about today is how we built our time series database. Get this cord out of my way. Talk about how we built our time series database and kind of some of the things that are different from typical time series databases, particularly open source ones, why we needed to build our own, why we built it on top of MySQL, what's great about that, what sucks about that, those kinds of things. For us, time series data, there's a few different kinds of data that we really need to stitch together to provide a good view of what's happening inside of a system. A lot of it is just metrics from some source. We call it a host. That may be a host server, or it may be an operating system. So it's for us, there's like a host MySQL, and then there's the operating system host that runs on, and we count those as two separate hosts, and they get assigned a number. So all of the metrics that we take off of those, the metrics might be something like CPU utilization, that kind of thing. But we assign them, label them with that host, the metric name, and then timestamps and values. And all of our timestamps are Unix timestamps. It's just a number, the standard Unix epoch timestamp. And the values are floating point values. And so we end up, we do all of our metrics are at 1 second resolution, so we get lots and lots of things all just synced on the clock tick. And there's lots of other kinds of time series data, right? So there's all sorts of stock ticker data. People generate time series data from logs or from events, like a web analytics would be a particular user at a particular moment in time was viewing a particular URL, and all kinds of other dimensionality that goes along with that. Our time series data is high dimensional in the sense that we're measuring lots and lots of things, but low dimensional in the sense that we call each of those things different metrics. So some systems will have like a multi-dimensional event. The event will be, let's say, a page view, and it will have a user or whatever the user identifier is. It'll have the browser, have the exact timestamp, the URL, perhaps several different metrics about the page load time. So there can be a type of time series data that's just very high dimensional events that are timestamped in time. What we're talking about is lots and lots and lots of things that are single dimensional, and they have a source that we measure them off of, and a metric, and then timestamps and values. And I've dealt with a lot of different time series databases over my career. I built a bunch of templates and a sort of a meta system for making templates for Cacti, for example. That lives on as Percona monitoring plugins these days. There's Graphite, which has the Whisper time series database behind it. ROD Tool is behind like half of the world's monitoring systems. ROD Tool, despite its popularity and despite it actually works very, very well. It wouldn't work for our kind of a scenario because everything is pre-allocated. You have to say in advance, I have this metric that I'm interested in, and go create me a file, and then I'm going to push metrics into that file. And our time series data doesn't have those kinds of characteristics that we can do that. Other popular ones, if you're not going to use those, people sort of different communities of people will have their default go-to, which will be HBase or OpenTSDB on top of HBase, or Cassandra, or OpenTSDB clone on top of Cassandra. InfluxDB is one that's kind of up and coming from somebody who built, the founder of InfluxDB has previously built like 3 or 4 time series databases on Cassandra. And there's a few others. And you can generally take a lot of different kinds of relational databases and sort of wedge time series data into it. And as SQL and SQL support in various databases gets more sophisticated, that becomes less and less awkward. Like it's less awkward now in Postgres than it used to be, for example, with windowing functions. And that continues to get better and better. But still, there's lots of kind of very specific time series databases that take one kind of point of view on things, like ROD Tool and all of the many clones of ROD Tool. And then there's generic things like relational database or Postgres or something like that that you might be able to apply to your use case. But there's a lot of time series use cases for which there isn't anything that's really optimal. And so a lot of companies like us build something in-house. I know, just to name some names, we've built our own. Circonus has built their own. A company called Tempo IQ, which used to be called TempoDB, used to use HBase. They've built their own internally. Interana has built their own. You know, and then you can look around at companies like Facebook with their Scuba stuff internally and so forth. And they're not using open source, purpose-built time series databases. Their use cases are such, and performance and availability and volume requirements are such that something breaks, and there's really no applicable solution. You have to build your own. So what's, I think, kind of interesting about us, that we've built our own on MySQL. And partly because I know MySQL pretty well, and I know how to make it work fast, and it's usable for lots and lots of other stuff, and we'll talk about some of the other reasons. But when you get really big with stuff, almost everybody has a homegrown time series database. A couple of others that I know, you know, there's a massive one inside of AOL, and I know the people who wrote it. Similar with Comcast, et cetera, et cetera. And what ends up being I interviewed a bunch of them, and they all told me that the thing that bit them after a while, you know, they all sort of just ran the ship into the shore and just could not go any farther with the available technologies and had to build their own. And I said, what's your one regret? And they always said their one regret is that they left behind an expressive query language that lots and lots of people could use. So it becomes the system of record for, you know, if you're an ISP, becomes the system of record for billing, for example. And now finance and marketing and everybody wants to do reporting out of this system of record. And they have to get the developers involved because there's no query language. And that's kind of the millstone of the custom homegrown time series database that hangs around everybody's neck who's ever built one. Our time series data, you know, everybody's time series data is a little bit different. Our time series data use case isn't going to be the same. Like, I haven't found anybody else who has the same requirements and constraints as we have. We're probably most similar to New Relic, and I learned a lot from studying how New Relic had done it, and I helped New Relic at various points as a consultant. So I learned some lessons, and I made some of the same mistakes and added some new ones. But New Relic is probably the most similar use case to us that I know of. You can think of VividCortex as New Relic, but specialized for the database in some ways. So as I mentioned, a host where we measured the stuff from metric and timestamp and value. And there's lots of metrics that are the standard things that you think about, like the CPU, I/O, disk space, network, that kind of stuff. Those are a relatively small number of metrics. They're static. You know they exist in advance. You know that no matter what, the CPU metric is always going to exist. So it's a very dense metric. And at any time that you sample it, you're going to get a value. So every second, we sample these metrics from everything, from the proc file system, for example. And we know that we're always going to get a CPU metric. It's something that we can know about in advance. It's not dynamic. It's always there. But then there's the stuff that comes and goes. So if we're generating metrics that are related to types of queries that people run, which we do, that's the bulk of our data, some queries are running a lot, and so they'll be, the metrics about them will be dense. Other queries, you might see one instance. You know, somebody writes an ad hoc query against the database, and then it never runs again. So you now have a metric, a little snowflake metric at a point in time. It's very sparse. There's only measurements occasionally, and the characteristics, you know, you don't know in advance what metrics you're going to see because it completely depends on what query traffic comes to the database. So we encode those dynamic things into the metric name. So I have here host.queries.hex blobby thing, and then a dimension about that. And we'll generate pretty high dimensional metrics about that. So we'll have tput for throughput. We'll have time in microseconds for the total time elapsed. We'll have an average latency over the sampling period, those kinds of things. We'll have error rates. There's another kind of variability because you don't know what kind of errors you're going to see. We measure per type of error. So error foreign key doesn't exist, or error, you don't have permissions, all of those different kinds of stuff. So you have very highly variable portions of the metric name. And that hexadecimally blob thing, we generate from digesting similar queries together and then MD5 summing it. So that's essentially an MD5 sum of the query digest. And then we generate metrics per lots of other stuff, per database, per user, per host that the queries are coming from, lots and lots of different things. And lots of metrics is great, but metrics do not tell a complete story. There's a whole bunch of other, in addition to this metrics time series data, we also capture, we probabilistically sample individual occurrences of queries and record them in their exact details without aggregating them together. So we will occasionally have those individual samples of queries that I showed you. And that's time series event data as well, but I won't talk much about that today. I'll talk mostly today about this time series metrics data. So the dense and sparse metrics, I've kind of already covered the content of this slide. But you'll always have these dense metrics. The sparse metrics are where the trouble really comes in, because we can get very, very high cardinality of that. A couple of things that are not completely unique but are rather unusual about what we do is really high resolution metrics. And for me, 1 second resolution is the minimum. I'd really like to be doing probably, I think 1 second is enough for humans. If you really want detailed information about what's happening about systems, I know people who do system introspection at the nanosecond level, for example. But I think probably 10 samples a second is even better than 1 second. But 1 second is already several orders of magnitude more than your typical monitoring system. If you think about most of your monitoring systems, you'll get 1 minute resolution at best. Like ROD-based systems, you'll typically get 1 minute at best, and that's usually only if you configure it that way. So Cacti comes out of the box with 5 minute resolution by default. And a lot of bad stuff can happen in 5 minutes. You can have 30-second outages in 5 minute metrics, and you will never see it. Even in 1 minute resolution, you just do not see enough detail. 10 second is kind of getting acceptable. 1 second is much, much better. And then we have a large number of metrics. So we don't have, like in a system like Cacti, you might have, if you're using the Cacti templates that I wrote, you might have 100 or 150 metrics that you're gathering about CPU and so forth and so on. In our system, we will typically have anywhere from tens of thousands to tens of millions of metrics per system. And if they happen to be dense, that ends up being a lot of metrics per second as well. So the kinds of questions that we ask of our time series database are also not just draw me a chart of a metric. If you think about something like a typical monitoring and graphing solution, you're usually looking at, let me switch my slides here. I'll switch back to, and where's my mouse? There's my mouse. So this will be a typical monitoring and graphing system. You'll have a bunch of little square tiles on this, or rectangular tiles, and then you'll have, like this one has 1 metric on it, and that's predefined and known in advance. See some disk metrics. Okay, so this one we've got 2 metrics on. This is your typical monitoring system where you have predefined graphs of a single metric. And that's one use case for a time series database. Give me a metric or 10 metrics or whatever from point A to point B in time, which is fine. But that is not what ends up being the bulk of our workload at VividCortex. What ends up being the bulk of the workload is the stuff that's necessary to generate these ranked views. With I showed you the top queries, the top processes, and so forth. And what we end up doing there is taking a time range and summing up those metrics over that time range and then ranking them. So top queries is take all of the queries by the dimension that you choose, such as the total time consumed, and rank them all up. You can think of it as like a group by order by some descending limit 10. And the cardinality of metrics that we might be doing that over, again, is potentially into the tens of millions. So it's not just looking at individual metrics. It's looking at very large numbers of metrics. And then across large numbers of hosts, I showed you on our systems monitoring ourselves, we had 59 hosts there. We have customers running many more than that. So you quickly have a lot of metrics that you're, to generate a view like that, you quickly are looking at a lot of metrics. And then you add in things like pattern matching and so forth. If you're looking at a particular SQL pattern that you want, you need to look up which metrics are related to that SQL pattern and so forth. So those are the difficult things to do. That's where stuff gets really sticky. What ends up being hard about that is that this is a system that's too large to fit onto a single server. And even if it fit on a single server, accessing way too much data to run in a single query, single-threaded. It has to be done in massive parallelism, even on single servers, but we parallelize across multiple servers as well. All of our APIs and our internal services are written in Go. Go makes it very easy to do a lot of work concurrently. And so we fire off, when you send a top queries request to our API, the API is actually kind of a thin wrapper around our time series database, which is not in MySQL itself. It's actually in a Go service internally. So we have an internal time series service that does the bulk of the work. Because it's distributed and has to be done in parallel across lots and lots of things at once, that logic has to come out of the databases. Somewhere it has to be done centrally, and the databases become kind of a dumb storage engine. So we're really not using a lot of smarts in the database server. We're not doing a lot of complicated group bys and order bys and limits and anything like that. That's not how our time series queries end up being resolved. What ends up happening is that you'll request something like, show me the top queries for all of these hosts by this metric, by this dimension. And so we have to go and figure out what are all the queries that exist in that time range for all of those hosts, and then we go to the database and ask for each database to give us its ranked total over that time range. So we do use the sum operator in SQL for that, but that's about as fancy as we get. And then it's a scatter-gather pattern. That comes back, all the results come back into the API's, the internal time series API, where they're aggregated up, and we take the top 10 or top 20 or whatever you've selected. And that's kind of how the time series queries end up getting resolved there. So we have to have a time series service that is suited for both these bulk scatter-gather types of queries in massive parallelism, and for those give me one metric over a time range and make it really, really quick, which is completely different sets of requirements and performance constraints. So that's where stuff gets interesting, in my opinion. Was your hand up, sir?
Do you have an index for the time series, or just a complete table scan?
So the question is, do we have indexes, or is it a full table scan? And it is indexed because and I'll get into how that doesn't always work well for every type of query. The individual queries over a particular range of time for a particular metric absolutely have to be indexed, because otherwise we'd be using a full table scan for a massive amount of data only to get a small amount out. But the indexes don't end up being very beneficial for the queries that are going over lots and lots of data at once. And a little while back, I just got the whiteboard out and did the math on what if we say screw the indexes when we're doing one of these bulk top queries, top processes, top whatever types of operations. What if we just scan it? get rid of the indexes, store it in a way that's optimal for scanning. And I did the math from the hardware up, pulled in a friend of mine to help double check everything. And we figured out that we were going to need about 2,000 servers with really, really high-end hardware to meet our performance constraints. So it's kind of like you're damned if you do and you're damned if you don't. The indexes don't help you enough, but there's way too much data to just brute force scan it, even in parallel. So I'll talk about how we're tackling that particular problem. There's a number of, yeah.
When you're saying the parallel part, you're sharding the time series database, right?
Mm-hmm.
Okay. And you're partitioning based on like the hash or the time itself?
Yeah, I'll talk about how we're partitioning it. So the question was, we're sharding and we're partitioning by time. Yeah, so we're doing both of those. We're sharding by environment. So this is a software as a service platform. It's highly multi-tenant, lots and lots of different customers. Each customer may have multiple environments, like they may have a staging environment and a development environment and a production environment, or they may have multiple production environments, like production in Chicago and production in LA or something like that. And all of our unit of sharding is currently the environment. So all of the data for an environment lives together. It's stored separately and strongly separated from everyone else's environments. But it is co-located on many of the same servers, so it's multi-tenant. So that's how the sharding works. And then how the partitioning works is we partition by time, as you guessed. And I'll talk about kind of how we started out doing that and what we're doing today and how that's changed and why. In fact, that's the next slide. So multi-tenant, sharded, talked about that. Separate databases. We also encrypt a lot of the data. So some of this data is sensitive. The data is not very useful unless you can understand what SQL it's related to. And yet SQL is typically regarded as pretty sensitive by a lot of the companies that we work with. Even sometimes metrics data is sensitive. Even though it's totally anonymized, a lot of companies are sort of hesitant to ship metrics data off to another company. So we have very strong security requirements and a very strong security architecture in place. Everybody's data is encrypted in flight end to end, and it's encrypted at rest. We have a blog post about how we do that. It goes into the Go language and how Go makes that really easy for us, which is a nice thing. And then we partition the data by time. We store 1 second resolution by default. It's a negotiable thing in a customer's contract, but we store it by default for 3 days at 1 second resolution, and then 1 minute resolution after that. Typically, people told us, I only really care about the high resolution data in order to diagnose recent events. After that, 1 minute resolution is plenty. Both of that's completely configurable. For our own environment, I like to keep 10 days of 1 second resolution. Yes, sir? I can't hear you. Can say again a little? Tell me if I'm saying this right. When we create a database, do we create both the 1 second and 1 minute resolution at the same time? We do this in a way that I don't think is optimal, but it was the quickest thing that we could get working. We write all of the data in from our services. It actually goes through Kafka first. So our APIs are just basically a short stop before heading into Kafka, which is a very fast, durable log. And then we have consumers reading the data back out of Kafka and putting it into MySQL. This way, if the databases are down, we don't lose any data. It gives us a lot of operational flexibility. And we populate the 1 second resolution tables currently from Kafka. And then we have this downsampling job that runs once an hour and turns that into 1 minute resolution. So I think that answers the question you're asking. Yeah. I would like the 1 minute resolution data to be built up to the minute. But the way that we store things vectorized, we store chunks of time vectorized together, means that we really have a sort of a fundamental batch unit of time. And so there's no way for us to write the most recent 1 minute resolution every minute. We need to wait until the hour is over, and then we can write a whole hour's worth in a batch. So we batch everything for efficiency. And we use InnoDB, which is, these days it's high performance. It wasn't always the case. It's always been extremely reliable and very durable, highly resistant to corruption. And it has clustered indexes, and that's important. So the schema design is a big issue. I knew in advance a lot of the things that we needed to do, and so we got a lot of it right up front. We got a couple of things wrong, and then we also learned that we and our customers wanted to do different things. We didn't realize up front all of the types of workload that we were going to run against our databases. So the schema requirements were discovered over time, and or they changed over time. And with a very large database, schema changes become difficult. Sort of understatement of the month, right? Kind of obvious thing to say. By the way, if I didn't mention, I will share the slides. So there's kind of two ways that you can index data, depending on what you want to optimize for the read path. We know it needs to be read optimized. It cannot be write optimized, because if you're going to generate those kinds of time series charts, they need to be generated very fast. That's kind of an expectation. And you can't be doing slow queries to populate those. So it definitely has to be read optimized. So the question is, should it be optimized for read by metric by time, or should it be optimized for read by time by metric, or both? And the cost of indexing is very real. You know, at scale like this, the cost of indexing adds a lot. It adds a lot of disk storage, and it adds a lot of, essentially, if you're going to index our data, again, by a different dimension, like if you're going to store it clustered timestamp first and then index it metric first, or store it clustered metric first and then index timestamp first, you're basically going to duplicate the space and the time requirements for it due to the indexing. So the question was, would we really be winning? Would we actually pay back the amortized cost of that indexing, or should we just do one dimension of indexing and accept the slightly less performant reads that come from reading in a way that's not completely optimized? Or do we just do something else? And as it turns out, I believe, and my past experience from other companies has been that optimizing for selecting a specific metric and then reading a range of time for that metric is extremely important. So for that, it means that we need to cluster our data metric first by host and metric, which you can essentially consider to be concatenated together to be a prefix of one another, and then by time range. So that means that the primary key for our table, which we call observation, did I have that table name? No, I'll have the table name in a later slide. That means that the primary key for our metrics table would seemingly be the most optimal primary key would be the host, the metric, the timestamp, and the value. I think I mentioned this, but just in case I didn't, we also, it's not a single value. It's not host, metric, timestamp, and value. It's host, metric, timestamp, and a bunch of values. So we cram them into a binary column and then store that all together in vectors. So the advantages of metric first is that it means that those dense metrics like CPU and so forth can be read very fast along any given time range. The drawback is that if we're looking at the sparse metrics over a particular time range, in a lot of cases, if we have, let's say, 10 million metrics that we're trying to rank and aggregate, a lot of those metrics won't even exist during that time range. And there's no way in a B-tree sorted index, other than a full scan of a big chunk of an index, to say, go and grab all of the metrics that exist in that time range, unless you, I'm not saying this very well, but you essentially need to create 10 million-fold in clauses. Very, very large numbers of specifically identified individual metrics. It's a really, really horrible, suboptimal use case for the database. If it were indexed timestamp first, the reverse would be true. We could take a time range and we could say just scan through that time range and add up all of the metrics that you find, whatever metrics existed. It doesn't matter if they're dense or sparse. Add up all of those, and then give us the top metrics during that time range. But that would not, and that would be optimal for writing metrics, because you would always be appending to the end. But that would not at all be optimal for reading a specific metric over a time range. So there's a fundamental tension between these two things. So secondary indexing, theoretically, we could build a secondary index. In practice, again, there was an open question about, are the queries actually going to be faster, and will we win back? We'd be paying a cost at write time for that. Obviously, whatever you do index, you're going to pay a cost at write time for it. So we tried. We tried both ways. And my experience has been that a lot of times you think something is theoretically going to be optimal, and you do all the math, and then you go and find out that in the end it isn't, whether it's caching effects or whether it's specifics about how the query is optimized or those kinds of things. The real world makes your theory not work out so well. And so we tried this. I knew that was the only way to figure it out. Just try a whole bunch of different ways with large volumes of data. And we figured out that indexing the data along two dimensions, essentially sorting it both directions at once, was not a win for us. That for these large, many metric timestamps bounded queries, a timestamp first index didn't gain us anything. All it did was penalize us with write amplification and space amplification. We thought about some other types of storage engines for MySQL. We thought about things other than MySQL. I'll talk about some of those later. But all of them had drawbacks, and some of those drawbacks are being eased these days. Like TokuDB is more mature now than it was 3 years ago. But still, we didn't find anything that was better than what we were doing. So partitioning is sort of a coarse time-first indexing, if you think of it that way, right? If we partition by time range. And so I said, well, let's just partition by day. We'll probably need to change that later. We'll figure it out as we go. This will get us started. So that's how we did it. We used MySQL's built-in partitioning on time range, a day at a time. And it made it easy for us to do specific things, like dropping old data when it was no longer needed is essentially a file system RM, just unlinking files. A lot of different kinds of purging strategies would involve like deleting and recompacting. Incredibly expensive. That's actually one of the reasons that we couldn't use InfluxDB, because deleting and expiring old data is as expensive as inserting it. So if you think about it, that's essentially twice the workload on your database. We want deleting old, unneeded data to be extremely cheap. The partitioning was transparent to the application, so that allowed us to not worry about querying lots and lots and lots of different tables, for example. So that was useful. The drawbacks come in, alter table. You can't alter one partition at a time. Well, that actually got better in MySQL 5.6. You could pull a partition out with an exchange partition. You pull that partition out, alter it, and then drop it into a new table. So we did a bunch of that. Spent and wasted a whole bunch of time on that over several of the alters as the application evolved. The partition maintenance, very easy little script, run once a day. Just delete the old partitions that you don't need. Look at the customer's retention policy and drop the old partitions and make some new ones. Make sure that you've got partitions for future data and things like that. Really, really easy. But because partitioned tables in MySQL are still considered to be a single table, even though they're composed of lots of underlying tables, there's still a global lock. So if there happened to be a runaway long query running, the partition maintenance operations would fail, and things would bottleneck and block and back up, and all the typical kinds of operational hassles. They're going to happen. You just don't know exactly which ones you're going to run into. So no particular exciting war stories about that, just the usual. Yeah.
Does each customer have their own set of tables in the database?
Each customer has their own database. Yeah, so they have their own set of tables. Mm-hmm. So eventually, death by alter table. we realized that we were spending more time hassling with alter table and hassling with partitioning than it was worth, and it would actually not be too hard for us to just write the partitioning, take the partitioning out of the database, taking basically all the intelligence out of the database and putting it into our time series service. Go makes that pretty easy. So what our table names now include what is the data, what is the resolution of the data, what is the beginning and end timestamp, and what is the schema version. So this allows us to stop altering tables to begin with. If we have an old schema version, it'll expire eventually. This table name here, observation 1, that's the schema version. Observation version 1. The S stands for second resolution. There are other tables that have an M for minute resolution. And then there's the time ranges of that table. And so if you do a show tables on our databases now, you get lots and lots of these tables with numbers and stuff embedded in them. No more whole table locking, no more altering. As we evolve the schema versions, we can just introduce version 2 tables, and until we expired the last of the version 1 tables from our data, we'll keep the version 1 logic in our time series service around. When all of that version 1 data is gone, we can drop that logic and redeploy that service. So that's a big improvement. I wish we had done that from the beginning. I thought it was going to be a lot harder than it was, which is why we went with MySQL native partitioning in the beginning. Go really helped us here, and as we got more confident with Go, it became easier. I wrote an ebook, by the way, about using Go with MySQL in particular, but with relational databases in general. That's on vividcortex.com. So there's a few challenges. One is this high ingest rate. If you're monitoring lots and lots of servers and lots of, potentially tens of millions of metrics per server, all at 1 second metric resolution, you're looking at just a very large number of metrics per second. And to deal with that, we have a variety of stuff that extends all the way out to the agents that are collecting the metrics. First of all, the agents batch things together before they even send them to our API. Secondly, we do a lot of things like we take counters that you only care about as rates, like queries per second. You don't care about the absolute number of queries that the status counter says your database has run. You really care about the rate over time. So we'll take those things and subtract them from each other. We get deltas. Those numbers are small, and they often turn into unchanging data. So there will be lots of the hundreds of status counters within MySQL, for example, that don't change. There will be some COM counter for some particular operation that changes only rarely. And so we turn most of those into zeros. And in a time series rate, 0 is indistinguishable from not there at all. So we can drop a lot of that data. That reduces the volume of data greatly. And to know whether we measured something or not, we have a timestamp or a heartbeat that happens once a timestamp. So, for example, you can choose a metric like system uptime. MySQL has an uptime status counter. If the uptime is 1 once a second, that means that the counter increased by 1 every second. So we measured during that second. And if we don't have a metric for something else of interest during that time, we know that we actually measured it, but if we measured it to be 0 and we just dropped it. So we can tell the difference then between 0 and missing metrics by using this little heartbeat mechanism. But we still get a large number of metrics arriving in our systems, very large. And that primarily comes from the combinatorial explosion of query-based and process-based metrics. So currently, each shard handles about 100,000 metrics per second. So that's very hard to achieve with MySQL if you're writing all of those things separately, which is why we batch them. We batch them going into Kafka, we batch them coming out of Kafka, and we batch them going into the database, as I mentioned. The drawback of batching stuff and storing it in vectors in a row, so the row essentially becomes wide with a bunch of columns in it, is that you lose the ability to query at the 1 second resolution with SQL. But in practice, we actually don't need that. We also, since we're batching metrics into 1 minute rows, even the 1 second resolution data is batched into 1 minute rows. The 1 minute resolution is batched into 1 hour rows. And we'll measure everything at those intervals, but then we'll also aggregate that up, and we have a couple of extra columns in each of those rows that tells you the total for the minute or the total for the hour. So sometimes we don't need to access all of the columns. For things like top queries, we're only looking at the sum for that minute. We're not looking at the second-by-second metrics. The other big deal is the metric names. If you're encoding the metric names in the rows, metric names are long, and they're variable. And it's much better to have fixed length rows and to have short rows. So we encode metric IDs. And we use MD5, and we did the math and figured out at what rate we could expect to get an MD5 collision. And even with only 64 bits of MD5, it's actually a very, very large number of metrics. Still has an incredibly low collision probability, so I was comfortable with that. We do have other mechanisms in case we ever end up with a collision, but not using like an auto increment ID for metrics, but instead using an MD5 sum of the metric name actually allows us to bypass the metric lookup table in a lot of cases. There still is currently, in those large bulk operations, there still is a step where first we look up all the possible metrics for, let's say, queries by time or queries by throughput or something like that, and then we do this scatter-gather with lots and lots of individual metric IDs. The solution to that is basically to prefix all of the metrics with a category, and the category represents the pattern of the metric, and be a little involved to get into it, but we can basically batch all of these, categorize all of these metrics together and give them a common prefix in the primary key. So we will be expanding our time series schema to include a category column in the near future. That's in progress at the moment. Challenge number 2, sparse metrics. I've talked about this. There's a huge cardinality of 100 million times 100 hosts. You're talking about a very large number of if you're building in clauses with metric IDs and host IDs, and it's just an explosion, combinatorial explosion. And since most of those metrics don't exist for those hosts during the time range that you're looking at, if they're sparse metrics, it's an inefficiency to even look for them. So then the question becomes, how can we eliminate and narrow down the number of metrics? So this is essentially a time-first existence index that needs to be built. And the way to build that, I think, we talked about a bunch of different ways. I mean, you could do it as an index, or you could do it as a very coarse kind of, a good enough approximation with buckets of time, like an hour at a time or 15 minutes at a time or something like that. We experimented with a bunch of different stuff, and we decided that we wanted to know hour by hour which metrics existed were measured to be other than non-zero during each period of time. So we chose hour by hour, and then you need to maintain that. And so as the metrics are flowing in from agents, if you see a metric, you basically need to go, okay, it's hour whatever, lop off the end of the current timestamp to the previous to modulo 3600, and then update that says, yes, we saw for this host, for this metric, for this hour, timestamp modulo 3600, yes, it exists. And then the next time you see that, you're going to say yes again. You don't want to be reading and saying, is that metric there? If not, then yes, it. You always just want to be going, yes, 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 yes. Well, for high-frequency metrics, that means that once a minute, since we're batching things into minutes, you're just going to be recording over and over and over again, yes, this metric existed during this hour, which is a huge amount of overhead in MySQL and InnoDB, because even if you're just changing 1 to be 1, it's still a transaction, right? It's still a query. It's very high overhead in MySQL. It's a hot row. You're going to run into all kinds of mutex contention and so forth around that hot operation. It's very inefficient. So we use Redis for that at the moment. And it works well in Redis, because in Redis, if you say something is true and it's already true, I mean, it's almost trivially inexpensive. However, now we have, I had a problem, so I applied Redis. Now I have 2 problems, right? So now we have another series of problems. We have to keep Redis and MySQL in sync. They have to agree. If they don't agree, we get gaps in graphs. the data may be there, but Redis doesn't say it's there, and so it doesn't look like it's there. And occasionally we've had bugs where, like we had a silly deployment bug. We do everything DevOpsy. We use Ansible to build all of our servers and so forth and so on. And we had an Ansible bug where we deployed a service and told it that its Redis time existence index was on the wrong server. So we got missing data in Redis, which looked like missing data it looked like we were dropping customers' data. We weren't really, but then we had to back up and reprocess all of that data out of Kafka. So, having anything more than a single source of truth is always a pain in the butt. So that's something that we're working on, and there's a couple of architectural changes that we need to make so that we can use MySQL, use the existence of the data itself as proof of the existence of the data rather than having something else meta sitting on the side saying, yeah, the data exists over there. So we're working on that. So how well does it work in the end? Ingesting lots and lots of data. It actually works really well. And I've been surprised at how well it works. And benchmarking us against people who have similar use cases, we ended up being several orders of magnitude more efficient. It's reasonably compact. The data doesn't take much space on disk. We are not using InnoDB compression, by the way. Tried umpteen different ways to Sunday to use various different kinds of configuration and all of this. You can read about how Facebook did their optimizations to InnoDB compression. It doesn't work for us, in part because our rows are so small. And we have lots and lots of rows, small rows, and that doesn't compress very well in InnoDB. And the overhead of compression and decompression ends up being pretty unbearable. So, we're for our, like I say here, for our 10 days of 1 second data and 90 days of 1 minute data, it's only 80 gigabytes on disk, which is really small, actually. The larger portion of that, probably about 80 to 90% of that is actually in query samples and other blobs, which are also not optimal to store in MySQL, and I've considered actually using TokuDB's version of MongoDB for that, because, again, schema changes and things like that. But keeping things simple right now has been a win, so just using MySQL for everything we can. Performance is really good as well. For those of you who saw me loading top queries across all of these hosts for the time range, we're able to satisfy those with high parallelism very quickly. And we use the kind of hardware that 5 years ago I was scoffing at. I was a cloud skeptic 5 years ago, and I was saying nobody will ever run a serious database in EC2, but everything is in EC2. It's all on EBS. It's like, sort of worst practices all over the place, and yet we make it work really well. And it doesn't cost us very much either. It's a lot less than buying our own hardware at the moment. And because everybody likes large numbers, at last count a month or so ago, we were ingesting about 28 billion metrics per day, which ends up being several 100,000 per second on 3 shards, essentially, which are relatively idle. The only time that we ever work them hard is when we do one of those bulk operations where we peg every CPU for a very short period of time in our entire environment. So we put every CPU to use when we do one of those. The good stuff about what we've built is that it's efficient. As a startup, you need to go with what you know works. And if you know there's nothing that works for you, sure, start evaluating things. But our first problem is not to build a highly available, high-performance service that's technically awesome and everything. Our first goal for the we're like 2.5 years old now, and our first goal for the first year or so was, do we have a problem that's worth solving? Do we have a problem, or do we have a solution that people are going to pay us for? Can we build a business out of this? So evaluating lots of hipster technologies or going with things that people said worked but didn't necessarily have existence proofs in exactly our use case was not a priority. What was a priority was just getting it done. I did evaluate and do the math on a bunch of things to see if we were overlooking something that would be a massive win for us. But in almost every case, I was either able to find that there was that we were much better, or I was not able to find a win. So I looked at Cassandra. I looked at lots and lots of time series databases that various people have written. And in most cases, and lots of vendors have pitched me, some of them MySQL-based vendors, some of them others. In most cases, you can just do the napkin math really quickly. Like I remember doing that with one vendor. The pitch was something like, well, Marketo uses us. Okay, Marketo is a big company. They have a lot of data. Marketo uses us, and they process X number of transactions per month. Okay, let me divide that by, figure out how many it is per second on X number of servers, and okay, let me divide that out to figure out how many transactions per second per server there are. Two transactions per second per server? Are you kidding me? So if I multiply that, very quickly I figured out I was going to have hundreds of thousands of servers of this vendor's product. I have 3 servers, 3 shards. That's not a win. Yes, sir.
What's the average CPU utilization you're looking at using on these servers?
I'll show you. Let's go look.
If only there were a way to see.
If only there were a way to see. So where's my mouse? There's my mouse. Let's look at all the shard servers. So I'll just filter by shard. And let's just look at CPU. And I will filter by utilization. And that is during that particular time range. Let's do over the last hour. And the last hour ending now. Practically nothing. The only time when we utilize these CPUs is during those very short bursts of time when we have a bulk operation going on. Yes? I'm sorry, I can't hear you.
How do you back up your data? Do you have a backup outside?
Oh, yeah, backups? Yeah, absolutely. There's a talk at Percona Live that we're going to give on our backup strategy. Short version is we use extra backup, then we encrypt everything, then we stick it into Amazon S3. Yes?
So what's the impact of the agent on the host that you're monitoring?
Let's see. I can show you that too. So let's go to top processes, and let's look for VC because all of them are VC prefixed. So there's this VC MySQL query, and system CPU is 6.95%. That's an 8 CPU box, so that's less than 1% of CPU. These others, VC OS metrics, that's like 1.5%, 2% of CPU. The others are essentially negligible. And the resident set memory is also, oh, and by the way, this is across 18 hosts, so divide that even by 18. So there's very, very little overhead. Our agents are written in Go. They use very little memory, and they use very little CPU. Yeah?
Since you are encrypting the data anyway in the application, why didn't you think of compressing as well in the application itself? Since your metrics are essentially numbers, and the compressibility should be really good, right?
Yeah, so the question is, since we're encrypting, why aren't we compressing as well? We are. Yeah, so we're our APIs, both the external facing APIs as well as the internal services. We have a highly service-oriented architecture. Everything is compressed and encrypted. Some stuff doesn't compress very well, and so we don't necessarily compress everything. But everywhere that we win from it, we compress and encrypt. And Go makes that really easy. There's a blog post on our blog about transparent encryption with Go. The same thing applies. It's like 2 lines of code to do transparent compression with Go as well. Yeah, so the agents are, we're doing a lot of heavy lifting with the agents. We're, for example, sniffing the network traffic with libpcap and decoding the MySQL protocol. We're reassembling packets and decoding the protocol and measuring everything. So it does a lot of work. And we've had to do a lot of very, very low level. It's not like just you got this performance by using Go for free. We have some very senior experienced programmers who know a lot more than I do. And we put a significant amount of work into optimizing things. In addition to not using much resources, we also have resource constraints. So the agents, if the agents, there's a supervisor agent. And if the agents use too much memory or too much CPU, kill them. So we have limits in place. That was important a year and a half ago. It never happens anymore. So we're running lean and cheap and getting a lot of performance out of what we're doing. Not so great. We've ended up spending a bunch of programmer time on schema changes. And if we wanted to do, it's the same thing I mentioned about everybody wishes that their time series data had an ad hoc query language. Well, if you want to do ad hoc stuff, our time series database is effectively a large distributed, very dumb MySQL storage engine. Like I said, the most advanced operation we do is a sum, and a smart Go service in front of it. And so, if you want to do stuff with with time series for internal reporting or something like that, you have to go against that service. It's a reasonably well-designed service with a nice, coherent user interface, and so we do have a lot of internal services that are talking to our internal time series service, but it's still not something that a human can just go, select group by order. We don't have that level of ad hoc queryability. And MySQL still has too much overhead. As a MySQL expert, if I do say so myself, I know where a lot of the overhead is, and I know that eventually, if we want to, since we're using MySQL in a very brute force and dumb way, we could get rid of the overhead of SQL parsing. We could get rid of the overhead of InnoDB. Our time series data has these particular characteristics that it's written once, it's never updated, it's written at the end, et cetera, et cetera. We could write something probably 2 orders of magnitude more efficient, but we would have to spend the time in engineering to do that. And for right now, MySQL is a very good all-purpose workhorse for us. The blob storage is still an area where there's a significant opportunity for us to win. So samples of queries and explain plans and all this kind of text storage that constitutes actually the majority of our data. So as I mentioned, we evaluated a whole bunch of alternatives, including Cassandra and so forth. I think in version 3.0, Cassandra is actually going to be something I will take another look at because of right now, Cassandra is not really a database. It's a distributed key value store that you can do gets and puts, and you can do gets along ranges. But you can't evaluate expressions like sum up along a range. If you want to sum up along a range, you're going to have to go and get the whole thing and forklift it across the network and do the summing up in some other process. Being able to push that simple operation of a sum inside of Cassandra would be a huge win, and that would completely change the picture for us. And that's potentially coming in Cassandra 3.0. The vendor pitches are often completely tone deaf, completely oblivious to the scale that we're operating at and the performance constraints that we have. A lot of these vendors are successful commercially because they solve a problem not necessarily in a very optimal way. And I'm trying to keep from accumulating a lot of baggage with a lot of technical diversity, and I'm trying to keep us from accumulating too many servers, because the more servers you have, the more data that you have, the more inertia and the more overhead you have in managing that. So we're trying to keep our data as small as we can. It's big data, quote unquote, but we try and keep it as small as we can. So that's everything, and I'm 24 seconds over time. But I'm still happy to answer questions. Yep.
My SQL server has, I'm coming from a DB2 American way. We call it rotation partition, which is able to rotate the old partition and then reuse the new partition.
Okay, so it sounds like DB2 has like round-robin partitions. Okay, so you can take the old partition and reuse it for new data.
Secondary DPSI, data partition second index. So you create time series, and then you can create index within that partition.
The way MySQL's partitioning works is that under the hood, every partition is a separate table that's managed separately by the storage engine, and every index is also separate. And the indexes only are local to each partition. There's no global index over the whole table. Yeah.
So they have
Yes.
Except to not have rotation, right?
There's no concept of rotating or round-robin partition in MySQL the way there is. It sounds like in DB2.
But that can be built by your applications. I build those
Yeah, we do. You would do it in the application, exactly. Yes. Sorry, I still can't hear you. This makes quite a bit of noise. So do we have failover? Yes, we do. Yeah, we have several failovers, and we have stuff across regions. So we're highly available, and we have standby systems to fail over to. Say again a little louder. We do have several copies of our data, yes. We don't have any problems with replication, no. No. It's not a challenge for us. A lot of the reason is that we've kept our data as small as we have. We also leverage parallel replication in MySQL 5.6, which works very well for our use case, partly because our multi-tenancy operates along separate databases. And so parallel replication works quite well. So no problems with that. One thing that would benefit us, because we're shipping our data across the country for, we have our primary data center in EC2 is in US 1A East, of course, in Northern Virginia, and our standby is in Portland. And since we are shipping everything over the wire there, it would be nice if binary logs were compressed in MySQL, but they're not. So, but you can use the client compression protocol to accomplish that in sort of a way. Anything else? Probably a good time to Max. So TokuDB, it's very interesting because the compression actually works well in TokuDB, and because indexing is better than it is in InnoDB. The problem is that since we are heavily multi-tenant, at the time that we looked at it, the file system layout was the blocker. It's sort of TokuDB's file system layout is like, it doesn't respect data directories the way MySQL wants it to, so we would essentially have this giant collection of files in one directory. And that's not very operationally good for us. For example, moving a customer from one shard to another or something like that, it makes those sorts of operations harder. And you start to run into things like file system limitations from number of files in a directory and things like that. So just the messiness of that. I think there might have been one other or a couple of other things. I talked in quite some depth with them, and I was very interested in working in our specific use case with them. But we're sort of pretty far down the road now. I mean, it's not like we would never switch, but it's working well enough as we have it. Yep.
What do you think is your next big challenge? New services are coming up and all this.
What's our next big challenge? That's a really good question. The next big challenge is that very large organizations, so we show a unified view of the entire system from the database's point of view, which is a view that you cannot get from any other system. And it's across multiple databases. We have several other databases which are not even relational on the way. And you get a single point of view onto all of this, like all of your MySQL queries, your Postgres queries. Very soon it'll be Redis queries and MongoDB and all these things in a single interface that you can fluidly drill down into and slice and dice. But the larger companies that have very complex applications with small teams working on small portions of them have said, I don't want my developers are not going to be able to use the product if they have to look at everybody's workload and try and pick their own out. So we need even more slice and dice capability, which I started to realize there are time series databases like OpenTSDB that have this concept of tagging. It's essentially dimensionality and facts about metrics. And I've started to realize why. Now, one of the next steps for us is going to be building that dimensionality in a time series way. So, for example, this query is issued by this user from timestamp A to timestamp B, and then maybe the user changes. This query is related to this application or portion of the application from timestamp A to B, and then it changes, something like that. I think I should end now. I don't know if anyone else is speaking immediately after me, but I should probably end and follow up in the hallways.